All right, let's jump right in. Today, we're taking a deep look at the hidden structure that controls how quickly a complex system forgets its past. We're going to be exploring the geometry and the analysis behind a really critical number, the mixing rate, all based on the work from paper 40.
So first things first, what exactly is this mixing rate, this number we call sigma? Well, imagine pouring cream into your coffee. The mixing rate is basically a measure of how fast that cream swirls around and blends in until you've got a perfectly uniform cup of coffee. For chaotic systems, it tells us how fast the system forgets where it started and just settles into its natural long-term state. A bigger sigma means a shorter memory, which means faster mixing. Now, previous research, specifically in paper 39, actually set a kind of universal speed limit for this system. It proved rigorously that no matter what you do, the mixing rate sigma is always greater than or equal to about 0.1370. And that was a huge, solid result.
But you know, that just begs the question, right? Is that number the absolute final limit? Or is there some kind of hidden structure, some deeper organizational principle we haven't seen yet that could let the system mix even faster than that? And that's the big mystery we're going to try to unravel today.
So to get to the bottom of this, the research really laid out two totally different paths for us to follow, two ways of looking at the same problem. You can think of it like a detective story, right? We've got two separate lines of inquiry, and both are trying to find the truth about sigma. On one side, you have the analyst toolkit. This is the safe and reliable route. It uses a very well-established mathematical tool, the Lasota-Yorke inequality, to give us proven, totally unconditional facts about the mixing rate. Then, on the other side, we've got the geometer's vision. This path is way more ambitious. It totally reimagines the problem using these new geometric shapes called cones, and it promises a way to potentially shatter that old speed limit. But, and this is a big but, its findings are conditional. Okay, let's kick things off with that first, more conservative path, the analyst's toolkit. This approach really grounds us in what we can prove without making any extra assumptions. At the very heart of this route is the Lasota-Yorke inequality. Just think of it like a fundamental rule about stretching and distortion. The system takes some initial state, and yeah, it stretches it and pulls it, but this inequality puts a hard limit on just how much stretching it can do. It gives us a guaranteed, rock-solid floor for the system's behavior.
So what do we get from this? Two absolutely crucial, unconditional facts. First, Theorem 1.3 shows us that the real mixing rate is always faster than the rate that the Lasota-Yorke inequality would predict on its own. And second, Theorem 1.4 gives us a precise formula that connects the mixing rate to that same constant and something called the system's spectral gap, which is really just a measure of how distinct the system's main behavior is from all its other potential behaviors. These are solid gold results, no ifs or buts attached.
Okay, now for the really ambitious part, let's switch over to route 2 and see how it builds on all this in a completely different direction. This approach reframes the whole problem, trading those inequalities for geometry. The secret weapon here is something called a positive BV cone. So what the heck is that? Well, it's basically just a special group of functions that we know are always positive, always well-behaved. By deciding to only look at what happens inside this cone, we get to ignore a lot of the more chaotic stuff and use some really powerful geometric tools. It's kind of like putting on a pair of special glasses that only let you see the most orderly parts of the system.
And you know what? This geometric approach has a huge unconditional win under its belt. Theorem 1.1 proves that if you stay within a specific sweet spot of the system's parameters, the system's operator, that's just the rule that moves everything forward in time, it always takes functions from inside the special cone and maps them right back into a nice, neat, smaller part of the cone. The geometric image it creates has a finite, predictable size. So this tells us that fundamentally the method is stable and it actually works.
So, what would it actually take for this whole geometric method to break the record? Well, it all boils down to a three-step recipe. Three key hypotheses that have to be true. First, the system has to keep everything tucked inside an even stricter version of that cone. Second, the shape that comes out at the end has to have a predictable, bounded size. And third, and this is the real clincher, the system has to actively shrink the distances between any 2 points inside that cone. If it can do all that, then we found something really special.
And here is the grand prize. If, and it's still a big if those three conditions are actually met, then this incredibly powerful result called Birkhoff's theorem just kicks in. And it guarantees, it proves that the mixing rate sigma will be better, it will be greater than our old record sigma max. This is literally the recipe for a breakthrough.
Now this all sounds amazing, right? Almost too good to be true. So why isn't this the final answer? Well, like any good detective story, there's a twist in the tale. And the problem, it turns out, is at the edges. This brings us to the million-dollar question, doesn't it? If this whole cone method is so powerful and has so much potential to break the record, why are we still talking about it with ifs and maybes? Why is it still a conditional result? And here's the roadblock. While everything looks super clean and controlled inside that sweet spot of the system, things get really messy when you get close to the boundaries of the parameter window. Near these edge values, the system's distortion can just blow up. It shatters that delicate geometric control that we need for the cone method to work. The diameter of our cone suddenly becomes unboundedly large, and we lose our grip on it.
But look, this is not a failure, not at all. In fact, this discovery is fantastic because it lets us refine our quest. It points exactly to where future research needs to focus its attention.
This deeper understanding really sharpens the whole investigation. It leads to a new, more refined set of conjectures. The main idea is that the geometric method should still work perfectly fine for all the points inside the parameter range, as long as we stay away from those messy edges. The theory suggests the mixing rate will stay safely above 0. It won't ever just flatline, as long as we're not right on the boundary. The problem isn't the whole system, it's just those critical tipping points. And that leaves us with this one really fascinating final thought. This entire investigation has zeroed in on the boundaries, on the edges, as the real source of the problem. So the question now becomes, if we can finally understand and control the geometry of chaos right at these critical tipping points, could we be on the verge of discovering universal laws that govern not just this one system, but all complex systems? The quest definitely continues.